previous module, I introduced you the perturbation method and said you that whenever the system is slightly different from the from a system for which the solution is known, we say it to be a perturbed system. And I also defined the what is the nth order perturbation, what is the first order perturbation, what is the second order perturbation. And I left you at these equations: equation number 7, equation number 8, and equation number 9. I would say equation number 8 and equation number 9. And I said you the goal is to find out the first order correction to the energy En1 and the first order correction to the wave function psi n1. And if you go for second order correction, then En2 is the second order correction to the energy and psi n2 is the second order correction to the wave function. So this is finding out these goals. If you look at these equations for lambda 1, this was the equation, and if you slightly rearrange, then you get psi n1 h naught minus En naught minus En naught. You have En naught here, and here also you have psi n1, here also you have psi n1, so it will become common. Okay, you get this one, and then you have En1 psi n naught minus h prime psi n naught, and this is equation number 8. Okay, then if you write this one, that's the equation number 8, then it is, you can rearrange to get this one, lambda psi n2 is equal to this one. You see, let me write it here, that psi n1 we say first order correction, perhaps I have not written it anywhere, first order correction to eigenfunction, and En1 is first order correction to eigenvalue. Here also, if you have psi n2, then it is second order correction to eigenfunction, and En2 is second order correction to eigenvalue. So our whole exercise will be for finding out the En1 and psi n1, and once we find out, then what will be the energy of the unperturbed system? Energy of the perturbed system. Energy of the perturbed system will be En, will be equal to En naught, which is the energy of unperturbed system which is known to you, plus En1, correction in the energy. So this will be the total energy. So same way, wave function for the perturbed system will be psi n naught plus psi n1, first order correction to the energy. So this way you get the total energy and the total wave function for the perturbed system, and we will restrict ourselves to the first order correction. I will give you the equation for second order correction also, but the derivation we will do for the first order correction only. Okay, so if you do the first order correction, then the total energy is the energy of the unperturbed system plus the correction. Total wave function is the wave function of the unperturbed system plus the correction in the wave functions, and then you get the actual eigenfunction and eigenvalue. This is how you get the eigenfunction and eigenvalue of the perturbed system. Okay, so if you solve this equation number 9, you get psi n2 and psi n1, and if you solve equation number 8, you get psi n1, first order correction to eigenfunctions and first order correction to energy, and if you do this one, you get psi n2, and En2 means second order correction. Okay, so getting the solution for first order perturbation, you start with equation number 8, and this equation number 8, by psi n1 is expanded in terms of orthogonal and normalized set of functions psi n1, psi 1 2 naught, psi 2 naught, psi 3 naught, and psi m naught. And if you expand this, what do you get? With the coefficients a1, a2, a3, then this psi n1 could be expanded to a1 psi 1 naught, a2 psi 2 naught, a3 psi 3 naught, am psi m naught. Okay. Same way, h prime psi n naught can also be expanded similarly. H prime psi n naught is this one. This also can be expanded. And if you expand this one, this you expand in this way. Okay. Now here h prime is written as h prime 1n, 2n, 3n and mn. Okay. And psi 1 is psi 1 naught, psi 2 naught, psi 3 naught. This in terms of psi 1 naught, psi 2 naught, psi 3 naught, the expansion is already on the equation number 10. Okay. If we use these two equations 10 and 11 in the equation number 8, what do you get? You have psi n1. So in place of psi n1, now I have written a1 psi 1 naught, a2 psi 2 naught, a3 psi 3 naught and am psi m naught. This is your psi n1. Then you have h naught minus en naught. So h naught minus en naught. Okay. This h naught minus en naught remains as such on the LHS. On the right hand side, psi n1 and en1 and psi n naught remains as such from the equation number 8. But this minus h prime psi n naught changes. H prime psi n naught we have expanded in equation number 11. So put that value h1n prime psi 1 naught, h2n prime h2 psi 2 naught, h3n prime psi 3 naught and hmn prime psi m naught. So this is the equation number 12. I've just put the values of expansion, expanded form of psi n1 and h prime psi n naught into equation number 8. And if you do that, then what you can write? Okay, what you can write is this one: a1 psi 1 naught, and the first term, first few terms. Let's see. Equation number 12 is not here, but the first term will be what? You will multiply this one, a1 psi 1 naught, with this. This is a common term, h naught, en naught. So let's see. First term is this. This is the term a1 psi 1 naught, h naught minus en naught. Then a2 psi 2 naught, h naught minus m. And same way other terms, and then am psi m naught, h naught minus en naught. So left hand side is very easy to do. Okay, left hand side you have one expansion, another is h naught psi n naught, en naught. So this term remains same, and if you multiply with 1, 2, 3 and so on, but I have limited the term, I have not used all, so this gives you this one. Then on the right hand side you have en1 psi n naught, en1 psi n naught will remain as such, en1 psi n naught will remain such, and the rest of the term will be like this one. So only thing is that we will multiply with minus sign, so it will be changed from plus to minus. So minus h1 prime psi 1 naught minus h2n prime psi 2 naught and so on, hmn prime psi m naught. Okay. Now what I say is that coefficients of psi m naught and psi n naught we too have. You have psi m naught also and you have psi n naught also. If you have psi m naught and psi n naught, should be same on both sides of the equation if m is equal to n. So if m is equal to n, just remember, if m is equal to n, then what do you get? You get coefficients of psi n naught. If you look at, then psi n naught is what? Psi n naught you get here, psi n naught. You get psi n naught here. This is also psi n naught because m is equal to n. Okay, and you have coefficients of psi m naught here also. Okay, so what do you get? If you compare this one, then this comes out to be en1 h prime nn, en1 h prime nn, and this becomes equal to 0 because psi n naught h naught, if you multiply with this one, what do you get? If you operate h naught on psi m naught, what do you get? You get em naught and psi m naught. So em naught minus em naught will be equal to 0. So this term will become 0. So LHS becomes 0, and on RHS you have h prime n. And what you can write is, you can write en1 is equal to h prime nn, which is actually this integral. psi n naught, h prime psi n naught d tau. Now in this integral, what is there? It is a wave function for unperturbed system that you know, because the exact solution is available. This is also the wave function for unperturbed system, the solution is known to you, and this is the perturbation or the disturbance. So from these, what do you get? You get En1 means first order correction to energy. First order correction to energy. This you get. So in terms of, so the first order correction to energy of the perturbed system En1 is equal to the expectation value of the perturbation parameter using the wave function of unperturbed system psi n naught. Why did I write expectation value? And if you remember expectation value postulate, it was psi m operator psi d tau divided by psi d tau. And if psi is a normalized function, then you write psi n, m operator psi n d tau, because this will become equal to 1, denominator will be equal to 1. So this, compare this equation with this equation, it is the same equation. Okay. So we have an operator in between, and on both sides you have psi n naught, and psi n naught is what? It is the normalized wave function for unperturbed system. So denominator will be equal to 1. It means it gives you the expectation value of corresponding to h prime operator. So whatever is the expectation value corresponding to the h prime operator, that can be determined by using the wave function for a unperturbed system for which the solution is already known. And then that value is called the first order correction to the energy of a perturbed system. So and denoted by En1. Okay. So this is the correction. Now if you compare these coefficients, then these coefficients are can be compared on both sides of the equations and can be written like this one. In first order correction to the wave functions, if you look at, then what is this one? Again, go back to the equation number 8, and this has to give you, now we are talking first order correction to energy we have found. We will get the energy here also, and our goal is to find out the first order correction to the wave function. Okay, so first order correction to the wave functions also, we can do the first order correction to the wave functions, and if I write this first order correction to the wave function means we have to find out psi n1. So psi n1 is expanded as a linear combination of orthonormal set of functions. Here also the similar expansions we do. Psi n1 is a1n psi 1 naught, a2n psi 2 naught, a3n psi 3 naught, amn psi m naught, and so it is a summation of amn psi m naught. This is expansion of psi n1, and then therefore this h prime psi n naught minus en1 psi n naught could be written as, is the same equation here, h prime psi n naught. If you bring it on the left side, this on the left side, so it is h prime psi n naught. Okay, then you have this on this left side, so with a minus sign you have en1 psi n naught, and then psi n1 is expanded like this one, so psi n1 is this one and h prime psi n naught. So it's the same equation, equation 8, where all the terms are on the left hand side. Now RHS becomes 0 and all these terms are here. So this I have brought here, this I have brought here, and it is these two terms, and along with the existing term of psi n1 into this one. Okay. Now if you have this one, the above equation is multiplied by a new function psi l naught and then integrated. So the whole equation you multiply by psi l naught and then integrate it. So what will be the integral? The first integral will be psi l naught h prime psi n naught minus psi l naught en1 psi n naught plus summation of amn, then again psi l naught h naught psi m naught, then summation amn minus with a minus sign, summation amn integral of psi l naught en naught psi m naught. So these will be the integral. 1, 2, 3 and 4 integrals you will have. 4 terms you have, so 4 integrals you will get. Okay. going by this, it's the same equation written here, and then you write this one. What I have written here? It is En1 eigenvalue, so you can bring it. Of course, delta is missing everywhere. Please write. Delta is missing everywhere. It should be there, volume element. Okay, and from minus infinity to plus infinity, everything will be there. I have just omitted it so that it looks simple to you. Okay, so you don't forget to, if you are writing in your exams, always write this delta and the limit also. Okay, that's there. So what you write? This equation is as such. Then En1 is a constant, so you can bring outside, and psi L naught, psi n naught, delta. Then summation mn, and then psi L naught, h naught. It's an operator, so this you cannot bring outside. But here again you have En naught, which is an eigenvalue, so you can bring outside. En naught you can bring outside. Okay. So now I write this equation is same, minus En1 psi L naught. Now h naught psi m naught, if you operate with this one, this is an operator for unperturbed system. An operator for unperturbed system operated on the wave function of an unperturbed system. This is also not symbol. It's a 0 given, but it is not symbol. So what does it will? It will give you Em naught psi m naught. So Em naught I have brought here outside, and then psi L naught, Em naught, psi Em naught. Okay, and then En naught, again this En naught is there, so this equation you get. Now if L is equal to N but L is not equal to M, what will happen? If L is equal to N, okay, so psi L naught h prime psi n naught minus En1 psi L naught psi n naught delta, then Amn, Em naught will remain here, psi L naught psi m naught minus Amn psi n naught psi L naught psi m naught could be what? This equation will be, you see, psi L naught h prime psi n naught is the same thing which I have written here. Now if L is equal to N, if L and L is equal, then this will be normalization condition will be equal to 1. So it will be En1 into normalization condition 1. If L is not equal to N, L is equal to N, but L is not equal to M. L is not equal to M means these are two different wave functions. So they are orthogonal to each other. The value will be 0. Here also L is not equal to M. So they are orthogonal functions. So this integral will be 0. So the rest of the two terms will be 0, 0. And what do you get? You get, what you get is this one. You see, you have psi L naught h prime psi n naught minus En1 is equal to 0. And if you bring En naught, En1 this side, then what you have? This one. This we have all. If in which condition? In the condition that L is equal to N. L is equal to N. So this you can write as En1 is integral of psi n naught h psi n naught delta. So what does it mean? It is the same equation which I said we derived for the first order correction to energy. We got the same equation here also, in this derivation also. Okay, and here it is the perturbation quantity, by what amount the system is perturbed. So knowing the wave function for the unperturbed system and knowing the perturbation, one can find out the first order correction to the energy. Okay, what else? Now if for the same equation, if L is not equal to N and M is equal to N but L is not equal to M, if you use this condition, then what you get is this one. First equation remains same. Now En1 becomes 0. Why? Because if you go back, for this you have L and N, and L and N are not equal. L and N are not equal. So it will be an orthogonality condition and you will have a 0 here. Okay. Now M is not equal to N, but L and M is equal. L and M is equal. So in the second condition you have L and M equal. So it will be normalization condition. So it will be equal to 1. Okay. This will also be equal to 1. L and M is equal. So you have this is equal to multiplied by 1 and this multiplied by 1. So the reverse has taken place now in this condition. This originally this was 1 in the first case and these two were 0. Now this is 0, these two are 1. Okay, these two integrals are 1. So what do you get? You get this equation. Psi L naught H prime psi N naught summation A M N E M naught minus E N naught is equal to 0. Okay. And from this what you get is, since L is equal to M, I have written L is equal to M. So what you can write? You can write, instead of M I have written L here. So psi L naught, psi N naught, now L N, L and N. M I have got rid of M now. Okay. Now this you can rearrange, and if you rearrange, what you get is A L N or A M N is equal to minus of psi L naught H prime psi N naught divided by psi L naught minus E N naught. Okay, where the condition is given. Since we expanded what? Psi N1, so psi N1 is actually this one. Psi N1 is minus psi L naught H prime psi N naught E M naught minus E N naught into psi M naught. This was the expansion, A M N expansion. If you remember first equation, let me go back because you should not forget this one. This was the expansion. This was the expansion of psi N1. So psi N1 is actually this one. A M N multiplied by psi M naught. So what you get is A M naught, A M N multiplied by psi M naught. So A M N value we found, and this is the equation. What is this? This is first order correction to eigenfunction. So on the previous slide we got the first order correction to energy, and here we have got the first order correction to the wave function or eigenfunction. Okay. Now so we can write this way. This is your formula for first order correction to the wave functions. First order perturbation we did both for the energy also and for the wave function also. Okay. So first order correction to energy is this one. Some just summarizing what we did. En1 is equal to psi n naught H prime psi n naught. First order correction to wave function is psi n1 is equal to psi m naught H prime psi n naught divided by En naught minus psi m naught multiplied by psi m naught. And second order correction to energy also you can find out. I have given you the direct value. We did not do the calculations, but I am giving you the direct value. See the difference between the En1 and psi m naught is, this equation is very similar to psi n1. Okay. So first order correction to wave function is this one. For this perturbation scheme to work, what is the condition? The condition is psi m naught is a wave function for unperturbed system. Okay. And I said you that it should be disturbed by a very small amount. So that small amount should come from this ratio. And we say that this ratio should be very, very small, very, very less than 1. Then only this scheme will work. And suppose if both psi n naught and psi m naught are same, then what will happen? Then this condition will not be satisfied. It will not be less than 1, it will be infinity. It will be very high. So then it will not work. And what do I mean by saying psi n naught and psi m naught is equal? I am saying about the degenerate state. So whatever you have learned is applicable only when you have non-degenerate states. So for degenerate state, a different mechanism, a different theory should be predicted. This condition is not satisfied when psi n naught is equal to psi m naught. Therefore, degenerate energy levels require a different approach from the non-degenerate treatment. So from this is all about non-degenerate time independent perturbation theory. Okay, where we have got the equation for first order correction to energy En1, formula for this one. You got the formula for En2 also, just I have written it, and you got the formula for psi n1 also, first order correction to the wave function also. So these three, the derivation apart, you must remember the relationship for these three, for en1, psi n2 and psi 2. And the good thing is this, that whenever you write en1, you don't have to bother about the wave function, because the wave function which you use is always for the unperturbed system, and this wave function is already known. So whenever you are asked to do a problem based on particle in a one-dimensional box, you know what is psi n naught. Whenever you are asked to do a problem on simple harmonic oscillator, you know what is your wave function for the simple harmonic oscillator. So that psi n naught is already known to you. The only thing which you have to bother about is the h prime, and then you can calculate the different corrections to the energy, corrections to the wave functions, and the total energy will always be the sum of the energy of unperturbed system plus the correction which you have calculated. If you have calculated up to first order, it will be psi n1. If you have calculated up to second order, then it will be psi n2. Okay. So this you have to remember, and some of the problems based on this will more clearly clarify your concept of time independent perturbation, and which we will be doing in the next module. Thank you.